We're looking at 9196 review worksheet number 2, continuing with number 10 here. Uh, the first thing we should always do if we're trying to determine if the series is convergent or not, we can test the nth term, test for divergence, and we see that if we rewrite this as x squared over e to the x cubed, the limit as x approaches infinity will produce 0. So that tells us that nth term test for divergence is inconclusive, and we look to our other options. Here, if we look at this form, I converted n squared to be in terms of x, and then I also made the negative exponent positive by bringing the e exponential function down to the denominator. This is in the form that we can use integral test for. And let's look at the conditions here. Function needs to be positive, decreasing, and continuous, and that's the case for this function. So we can try and go through integral test. So integral test, we identify the u value, go through u substitution. Our u value is x cubed, the derivative is 3x squared, dx equals du over 3x squared. We make our substitutions, going through u substitution, and we get 1/3 e to the negative u du. And if we go through integral, taking care of this improper integral here, integrand will become e to the negative x cubed, and then bring that down to the denominator, and then plug in our upper and lower bound, and this will give us the result as a real number. And if it's a real number, we know that because the improper integral produces a real number, the series must also converge as well. All right, number 11. We see that this is an alternating series, so all that needs to happen for an alternating series to converge is if the positive portion of it goes to 0. So the limit as n approaches infinity, we see that this denominator will keep increasing, causing the fraction to eventually approach 0. And then we also know that each subsequent term is going to be less than the previous term, and so that's enough to prove our series will converge by the alternating series test. Number 12. Since the limit as n approaches infinity, we have another alternating series here. As long as this portion of the rule of sequence goes to 0, the limit as this rule of sequence goes 0, again, that's enough for alternating series test to pass, and the series will converge. And that is the case here. The denominator is growing at a faster rate than the numerator, and eventually the limit of this expression will go to 0, and each subsequent term is decreasing. A sub n plus 1 is less than a sub n. Okay, not greater than. Less than or equal to a sub n for all n greater or equal to 5, so therefore series converge by alternating series test. 13. If we look at this here, first thing we do is test for nth term, and nth term is inconclusive. We don't have a nice way of determining using comparative growth rate which one is growing at a faster rate. We have exponential, we have factorial, so it's not very clear. So nth term test is inconclusive. Usually if we see exponential or factorial, then first thing we probably try and do, a good match is usually the ratio test. So ratio test says we find the limit as n approaches infinity for a sub n plus 1 divided by a sub n. So a sub n plus 1, we add 1 to each of the n values and divide it by a sub n, which is the same thing as multiplying by the reciprocal. So if we expand all these terms out, and we can see that eventually we see the denominator has a higher degree than the numerator, and so therefore we know that the limit of this expression will go to 0, which is less than 1. Less than 1 is the condition that needs to pass, and because it passes this condition, we know that by the ratio test the series will converge. Okay, the summation of sine of n. What happens with sine of n is that if we evaluate the limit as n approaches infinity, this expression the y value will continue to oscillate between -1 and 1. It will not settle on a value, and it will not, in other words, also it will not converge to 0. So therefore, we know that by the nth term test, it will diverge by the nth term test simply because the limit of this expression does not go to 0. Okay, 15. This is n factorial divided by 3n plus 2, or 2 times 5, all the way to 3n plus 2. So when we see factorial here, we can go through a ratio test, which is the a sub n plus 1 divided by a sub n. So a sub n plus 1, which is add 1 to each term, and divided by a sub n, which is multiplying by the reciprocal of a sub n. And if we see this, how these terms line up, n plus 1 factorial and n factorial will reduce to be just n plus 1. And then here, the denominator, all the terms will cancel out except for 3n plus 5. And so 3n plus 5, n plus 1 over 3n plus 5 will reduce to 1/3. And we see that 1/3 is less than 1, so series will converge by the ratio test. Okay, 16 here. We see if we go through nth term test, the limit of this expression will go to 0, so inconclusive. So we can possibly go through the ratio test again, but ratio test probably best fit for a factorial. So let's see, what about using the limit comparison test? So limit comparison test, we see that the relationship between numerator and denominator for the highest degree is the same thing as 1 over n. And if we do limit of the expression divided by one that we know will diverge, and it has a similar relationship with numerator and denominator, we can just see if this goes to be a real number. If the limit of this expression goes to becomes a real number, that means this series will share the same property of divergence as 1 over n. So if we simplify this expression, we can multiply the denominator, or we can bring this up as the reciprocal, so times n. So we get n cubed over n cubed, and that equals to 1. That's a real number, so by limit comparison test, since we know that 1 over n diverges, our series must also diverge since we're getting a real number in return. All right, 17. We know this is a series that oscillates between positive and negative. This is alternating series, so as long as this rule of sequence goes to 0, then this series will converge. However, 2 raised to the 1 over n, if we think about 1 over n, as n approaches infinity, this exponent will get closer and closer to 0. As it gets closer and closer to 0, 2 raised to the 0 is still going to be 1, and 1 does not equal to 0. So therefore, our series will diverge by the nth term test, since the limit doesn't go of this expression doesn't go to 0. There's no way that series will converge. So nth term test is enough to show that the series does not converge. All right, 18. This is a series that alternates, alternating series. So as long as this rule of sequence, 1 over square root of n minus 1, as long as the limit goes 0 and as long as each subsequent term decreases, then that's enough to show that the series will converge by the alternating series test. And if we keep increasing the value of n, we see that this expression will go to 0. And if we test out values increasing from n equals 2 to n equals 3, we see that each subsequent term will also decrease for all n greater than or equal to 2. So series will converge conditionally by the alternating series test. Okay, 19. We have alternating series. So let's see what happens with ln of n over square root of n. ln of n over square root of n goes to 0. Square root of n grows at a faster rate than natural log of n. So normally, this for nth term test would be inconclusive. However, because this is an alternating series, the only condition that needs to be met for alternating series to converge is if the limit of the rule of sequence goes 0, and if each subsequent term decreases and that is true. So therefore, the series converges by alternating series test.